Hey Anna, aren't you in my Psych 302 class?
Hey Emma, I guess we both decided to blow out some steam tonight.
I know, tell me about it. I've been so stressed trying to catch up with this class.
I know. Why are we even talking about the scientific method in class?
I have vague memories of hearing about the scientific method in high school. I know it starts with defining a question and gathering information. Then you come up with a research hypothesis, then testing that hypothesis by collecting data, analyzing the data, and then interpreting the data.
Oh, I bet the part about analyzing data involves stats.
I know there's even a tool in stats called hypothesis testing. It results in statistical conclusion, and that allows us to evaluate the research hypothesis and come up with a research conclusion.
Wait, you mean there's like a parallel world? Like there's a research hypothesis and a research conclusion, as well as a statistical hypothesis and a statistical conclusion?
Yeah, except that's sort of like the statistical world is embedded inside the research world.
Don't we have just one research hypothesis? It's weird because my professor talked about two statistical hypotheses, a null hypothesis and an alternative hypothesis. Null refers to nothing, so I guess the null hypothesis predicts that there will be no difference between the two conditions in the experiment, right?
That's the gist of it, but even more precisely, the null and the alternative hypotheses are the predictions about the parameters of the population. The statistical conclusion will be about those parameters, from then you can evaluate your research hypothesis. But hey, what are we doing? Let's keep our groove on. I love this song!
But seriously, what do parameters have to do with my conditions of my experiment?
Well, a null hypothesis usually says that two population parameters are equal. That's like saying that two groups are the same. The alternative hypothesis usually says that two parameters are not equal, so then the two groups are different.
That alternative hypothesis sounds like the research hypothesis, don't you think?
Yeah, often that's the way it is. So if the data supports the alternative hypothesis, then it also supports the research hypothesis.
Oh, but that sounds sort of like we're accepting the alternative hypothesis. But I think we're not supposed to do that. We're simply supposed to reject the null, right?
Oh yeah, you're right about that. But do you know why though? I've always thought that's made things extra confusing.
Well, it helps to keep in mind that statistical inference is based on probabilities rather than certainty. We reject the null when there's a very small probability that the null hypothesis is correct.
Oh yeah, that's where the alpha comes in, right?
Yeah, the alpha is like a standard of improbability. We're asking ourselves, if it is very unlikely that the sample came from the null population, then we should reject this hypothetical population.
Oh, so that's where the alpha is usually a very small probability, like 0.05 or 0.01.
Exactly. So if there's less than a 5% chance that the sample came from the true null hypothesis, why would we assume that the null is true based on the sample? That would be foolish. We would reject the null.
Wait a sec, the null can be true but we can reject it or fail to reject it, but also the alternative can be true but we can reject it or fail to reject it. It sounds like I have to juggle a bunch of possibilities.
Yeah. At the end of the hypothesis testing, you can potentially be correct or incorrect, but you can be correct in one of two ways, or incorrect in one of two ways.
Let's see, at the end of the hypothesis testing, you either reject the null hypothesis or fail to reject it. That we know for sure.
Right. We know our decision, but what we don't know is the actual state of the world. Either the null can actually be true, or it could be false.
So let's just say we decided to reject the null. If the null is true, then we just made a mistake. If the null is false, then we're correct.
I believe that kind of mistake is called a false alarm or a type 1 error. We decided there is a difference between two groups, but actually there isn't. It's like we decided to give surgery to someone who didn't actually have a tumor.
Okay, let me try an example. A false alarm in an experiment might be saying that a weight loss drug worked when the weight loss drug didn't actually work. I think that actually makes sense. That would be a pretty serious error on the part of science. But what if we fail to reject the null? Can we still be correct?
Yeah, if we fail to reject the null when the null is false, that's a good thing. That's like saying that we don't want to perform surgery on someone who is perfectly healthy. Unfortunately, those kind of studies tend to not be published.
Yeah, because that's like saying that a drug didn't work when it actually doesn't work. Usually people are less interested in finding out what does not work.
Yeah, I think that's also why type 2 errors or misses are also seen as less serious than type 1 errors. For instance, if we say that a drug didn't work, but it actually does work.
But I can think of situations where that is a serious error too. I mean, what if we're just sitting on a drug that cures some big disease, but we rejected the null?
Absolutely. Type 2 errors are very serious as well. That's why you have to consider the ramifications of both type 1 and 2 errors when we're conducting experiments.
So wait, then what is the p-value? Does that have something to do with these type 1 and type 2 errors?
The p-value is the probability of getting a sample statistic as extreme or more extreme given that the null hypothesis is true. So both the alpha and the p-value assume that the null is true.
So wait, then what is the difference?
Well, p-value depends on the sample. So in hypothesis testing, we start off by assuming that the null is true. We happen to get a particular sample. P-value is the likelihood of getting the sample or one that's even more extreme.
So if that sample is highly likely to have been randomly drawn from the population, then the p-value is very high. And if it's unlikely, the p-value is low.
Yeah, you got the idea.
So I guess that's just like saying that the p-value is the false alarm rate for a particular sample?
Yeah, you can think of it like that. For instance, let's say we have a sample that has a p-value of 0.08. That's like saying that we have an 8% probability of getting a sample that is different, or even more different from the null hypothesis, given that the null is true. It's a pretty small number.
But not smaller than 5%.
Right! Because it's not smaller than 5%, we're going to play it conservatively and fail to reject the null. We don't want to have an 8% chance of a false alarm, we will only tolerate 5%.
But if the p-value is very small, like 1%, it's like saying that the chance of getting the sample or a more extreme one is smaller than our set tolerance for false alarms.
Yeah, which means you should accept the alternative hypothesis, that your sample comes from some other hypothetical population.
Ah, you mean reject the null hypothesis. We don't really just say accept the alternative because our actual evidence just says that our sample is unlikely to have come from this null population. But that doesn't automatically mean that it's likely to have come from some other population.
Yeah, you got it.
You know, this helps because I can never remember whether the p-value should be smaller than or greater than 0.05. I realize now that I can just reason it out. It helps me knowing what the alpha equals 5% stands for.
Yeah, and it helps knowing what p-value means too.
Hey, I guess this class is not hard after all. Oh my god, don't turn around. But I think Dr. Sun is here and she's walking this way. Hey, shouldn't you be studying for the test? Oh no, run for your life, run!